Hey guys, we're back for 10.7 part 2, theoretical probability. So theoretical probability, on my page I made sure to make a little note that said only contains equally likely, I can write equally out, equally likely outcomes. Okay, so any occurrence for which the outcome is uncertain is called an experiment. The set of all possible outcomes is called the sample space of the experiment, denoted by S. An event, denoted by E, is the subcollection or subset of all of a sample space. Theoretical probability applies to a situation in which the sample space only outcome contains equally likely outcomes. So you're talking about things like rolling a dice, flipping a coin, things that you know have equally likely outcomes. Okay, computing theoretical probability. If an event E has n of E equally likely outcomes and its sample space has n of S equally likely outcomes, the theoretical probability of the event E is denoted by P of E, is the number of outcomes in the event E and the number of outcomes in the sample space. So the sum of the theoretical probabilities of all the possible outcomes in the sample space is 1, because we can't have a probability greater than 1 or they weren't equally likely outcomes. Okay, so example 1, a die is rolled. Find the probability of getting a number greater than 4. So we're going to start with listing out our sample space. So your sample space of a die is 1. You could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6. We're assuming this is just a standard die. So we know the number of events, n of S, so the number in our sample space, is 6. And then we have our events. It's a number greater than 4. So event E, a number greater than 4, well, there's only 2 numbers greater than 4, 5 and 6 on a die. And so we know that the number of events is 2. So the probability of our event occurring is going to be our number of our events, which is 2, over the number in our sample space, which is 6. So getting a number greater than 4 is going to be 1/3. So this, again, is theoretical probability, just a standard die, where all of it is the same. So next up, you have a try it yourself. And here, we have a die is rolled, find the probability of getting a number, find prob. Of getting a number less than 5. So our sample space again is 1, 2, 3, 4, 5, 6. The number in our sample space is 6. And then our event, so number less than 5, that's 1, 2, 3, 4, not including 5. So the number in our event space is 4. So we want to find our probability of E is n of E over n of S. So that gives me 4 over 6, which is 2/3. Okay. Let me know if you have a question on this group. So our next try it yourself says 2 ordinary 6-sided dice are rolled. What is the prob of getting a sum of 8? Okay, so I'm more visual, you guys know this. I find it easier to look at it as you have dice 1 roll the 1, dice 2 roll the 2, dice 1 roll the 1, dice 2 roll the 2, dice roll the 1, dice 2 roll the 3, Dice 1, roll the 1. Dice 2, roll the 4. Dice run, roll the 1. Dice 2, roll the 5. Dice 1, rolled a 6. Or roll the 1, and dice 2, roll the 6. And then doing the same thing. Well, dice 1, roll the 2. Dice 2, roll the 1. Dice 1, roll the 2. Dice 2, roll the 2. Dice 1, roll the 2. Dice 3, roll the 3. Dice 1, roll the 2. Dice 4, roll the 4. Dice 1, roll the 2. Dice 5, roll the 5. Dice 1, roll the 2. Dice 2, roll the 6. Okay, so you're seeing I'm struggling saying these. So I'm just going to list them out so you can see it. First number is dice 1. Dice 2 is the second one. So here we have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Okay. Now we want to know how many are in this space. So our n of our sample space, this is all of our possible outcomes for our sample space. Instead of listing them out in those brackets, so n of s, how many do we have? Well, we have 6 plus 6 plus 6 plus 6 plus 6 plus 6, which gives you 36. And I know that looks a little bit like a, so I'll try to change it. Okay, so we have 36 there, and then we want to know a sum of 8. So 6 plus 2 is 8, 5 plus 3 is 8, 4 plus 4 is 8, 3 plus 5 is 8, and 2 plus 6 is 8. So those are my only ones in my event space. So n of e, we have 1, 2, 3, 4, 5 is 5. So the probability of this event is going to be 5 over 36. Okay, so the probability of an event not occurring. So the probability that an event, E, is not occurring is equal to 1 minus the probability of the event will occur. So if you know the whole sample space is 1, if you take out the part that you know will occur, the rest has to be what doesn't occur. So, example, so find the probability of an event will not occur. If one person is randomly selected from the world population represented in the figure, find the probability that the person does not live in North America. Express the probability as a simplified fraction and as a decimal rounded to the nearest 1,000th. So, we want to find probability doesn't live in North America. And this is equal to 1 minus the probability that they live in North America. We could do it the other way, but it's much more time consuming. We'd have to add up all those fractions. So I can do 1 minus the probability that they live in North America. Well, we're not going to put it in millions, but we know that that's right here. 550 million, so I'm just leaving 550 over the total. And we know that the total is given on here somewhere. Well, nope, we got to add it up. So we're going to add up 400 plus 30 plus 4,230 plus 1,040 plus 750 plus 550, and that gives me 7,000. So, okay. So I end up with 6,450 over 7,000, which is 129 for 140, which is approximately 0.921. So you can write it as 92.1%. It says as a simplified fraction or as a decimal. So as a decimal, it would be this one. And then the fraction would be that 129 for 140. And so that is the probability that they don't live in the United States. We're going to skip the next, try it yourself, just wipe it out. Okay, so this is the end of day 2.